What we're going to cover in the second part here is more towards some recent architectures that have kind of contributed evidence to attention's efficacy. This might be a little bit intimidating and complicated, and from the back of the room you probably can't even see it. But this is the transformer architecture, and I'm going to break it down into its kind of component pieces, which are all really quite simple. But before I do that, I just want to introduce some visualizations that I use. The first thing is Kris's slides use this really beautiful curve to express a sequence and generation. I'm going to do a much more ugly but simple depiction, which is where each of the elements of your sequence is represented as a vector, which goes into the depth dimension here. And along the width, we have the different tokens. Tokens, you can think of them like words or perhaps characters. In reality, they're kind of like sub-pieces of words. The other thing I wanted to show you was, this is such a spoiler, I'm sorry. Okay. Yeah, so this is what I want to show you. So this is a attention matrix. On one side, we have our source input sequence going down the rows. And along the columns, we have our target sequence, or the thing that we are attending to. The lightest patches kind of express this first token of our input is attending to this token of our output. So that's saying that this first input is related to or cares about this particular output. Does that make sense? Yeah. So I'm going to be asking, does that make sense a lot? Because I'm a bit awful at explaining things, and just put your thumb down if it doesn't make sense. I can say things like in 10 different ways, and I think it'll make it a lot easier if you express, like, say it again, repeat it, put it in a different vernacular. Okay, so back to the beginning. Okay, so the transformer. It's become pretty popular recently. It introduces two mechanisms and borrows a lot from what was going on in generative modeling at the time. So the two mechanisms that it introduces is this multi-headed attention and self-attention. So I'm going to get into that. The second thing that it's exploiting is fast autoregressive decoding. And so if you've heard of autoregressive models, great. If you haven't, basically the idea is super simple. It's saying that for each element in your output sequence that you're generating, you want to condition on everything that you've generated before. So there's the other option is for each element in your output sequence, you could condition on the last one you generated, in which case you don't see everything before the most recent generation. But these models, what's kind of powerful about them, what gives them their expressive power is the ability to reference everything from the past. So positional encodings. I don't know why I started with this one, and I'm just not going to. I'm going to skip ahead to self-attention and multi-head attention, and we'll come back to positional encodings because from Kris's talk, you heard a bit about content-based and location-based attention. And so this first thing that I introduced, it's going to give us an obvious way of doing content-based attention, but it's going to have no mechanism for positional attention. Right, so self-attention and multi-headed attention. The typical attention that we think about, it relates elements from a source sequence, like your input, to a target sequence, like the targets you're trying to generate as output. So we can say that the first element of a source sequence is related to the second element of a target sequence, and for each of those elements in the source sequence, we're going to pick one in the target sequence. It Doesn't need to be one-to-one. You can have overlaps. You can ignore tokens completely. It's just whatever the model learns. So the idea with self-attention was make both the source and the target the same, or give them both to the attention mechanism. Yeah, so what this does, what's the intuition behind self-attention? A lot of the time, elements in our sentences, they relate within the same sentence. And so when attention was introduced, it was between separate sentences in different languages, or looking back over what you've already generated. But what's important is actually tying pieces of a sentence together. So for instance, if you have an adjective referring to a noun, like a blue chair, you want to tie that blue as referencing that chair. And you want to learn these kind of structures. Is that clear? Yeah. So basically you build up these within sentence connections. Each element of your sentence connects to another part, a different part. It could even point back at itself if it's kind of independent and only related to itself. So the second part of this is multi-headed attention. So previously, attention had only been done with a single head, and what a head is kind of like a copy or a parallel duplicate. And so when we do attention, we say, okay, this element in the source sequence is related to this element in the target sequence, so on, and you have this kind of one relational structure. You get, for each element of your source sequence, a particular element of the target sequence to which you're related. But there's only one relation that you're really expressing there. So with multi-head attention, what we do is we take our sequence, which are these vectors, we go ahead and we're going to split them up along the depth dimension. So if like each of your words is 32 dimensional vectors, then maybe you're going to split it up into 4 pieces, which is 8 dimensions in each piece. So you're going to do something like this, and then what we do is we pass each of these individually and in parallel to a separate attention head. And so now we can still relate elements of the source to some target, but instead of only having one particular relation, you have as many relations as you have heads. And what's kind of interesting, like just as an aside here, is that it turns out the multi-headed attention part is probably probably the most significant part of the transformer paper. A lot of recent experiments, they've kind of gone into how do we scale up these architectures. And what we've seen is that the number of heads almost completely dictates your performance. So if you come up with ways to more efficiently compute more heads, I mean, right now we're at like 8. 8 heads is kind of the standard. I think the largest have gone to 64. But if you can come up with efficient mechanisms for expressing more relations, that's a huge opportunity to kind of scale this up and boost performance. Right, so then after you've gone ahead and you've computed these self-attentions in each of your heads, you get out similar sized blocks. All you have to do is concatenate them all together and pass them forward to some future layer. Great, okay, now let me see if I can do positional encoding. So, right, so how do we compute similarity between elements? How do we compute the actual attention heads? I'm not sure if it was covered in Kris's talk, but what we actually do is if you have this sequence of vectors and you basically compute the outer product with itself, what you're doing is you come up with that attention matrix that I showed, which computes something proportional to the cosine similarity between all of those vectors. I wish I had have drawn this out. I regret not doing that. But what you do is you're going to say, okay, if this is my source sequence and target sequence, take this vector, inner product with this one, with this one, with this one, with this one. That's a row. And now you do that for each one of these, and you stack those rows on top of each other, and you get that matrix of like how aligned is each of the vectors in the source sequence with each of the vectors in the target sequence. Does that make sense? That is clear. Is it not clear for anyone? Okay, great, sweet. Easier than I thought. So the positional encoding. So with that was like purely positional, right? There was no notion of where it sat in the sequence. You were just taking arbitrary index in sequence 1 and comparing it to arbitrary index in sequence 2. You have no idea like where they sit relative to each other. You don't know, yeah, like the distance or anything like that. So what we need to do is introduce some mechanism which lets you compute relative distances and absolute distances. So an absolute distance is like from the beginning or the end of the sentence, how far are you? And then a relative distance is like relative, so if I'm comparing an element in the source sentence, which is at index 5, relative to index 5, the target vector that I'm comparing to, where does it sit? And so the way we do this is by introducing sine and cosine waves through these vectors. So basically you can append on the end or just add to them a sinusoid and a cosine wave. And we know from trig identities, I'm sure, that you can pan ahead in a sequence to any other position just by a linear combination of those two waves. So you can basically say, all right, so if I'm in position X in my sequence, just a linear combination of position X's positional encodings produces a pan ahead, k steps ahead. So now I have this notion of relative distance, and I can look at my own absolute, where am I in the sequence, just by referencing the positional encoding at that point. So now we have both a notion of relative distance and absolute. Does that make sense? Not so much? Okay. No, okay. So, right. Linear functions are a core piece of deep learning. They're super easy for us to do. They're just a matmul. And so what we really care about is an efficient way of panning forward. Turns out there's this identity where we say, if you have a sine at some point x and a cos at some point x, you can basically scoot ahead to sine at x plus a theta only by multiplying by some weights and then summing them together. Just doing a linear function of a cosine and sine wave, you can basically skirt ahead a discrete amount. Does that make sense? Great. Okay, so in our case, what we're doing is we're appending to the dimensions of our inputs two waves, a sine wave and a cos wave, which basically gives you the opportunity to say, okay, if I'm at position blah in the sine and cos, I can skirt ahead a particular amount. And why is this important? So the reason this is significant is because if you can manipulate your own positional embedding, if I'm the word blue, and I know that chair, or I predict that chair is going to follow me, so I want to see one step ahead. I'm just going to take my own positional encodings, the cos and sine at my position, apply this weighting to it and sum, and then I'm now more similar. I've changed my vector to be more similar to the one adjacent to me, which we hope is chair or whatever noun we're describing as blue. Does that make sense? Sweet, okay. Okay, we already did this. Okay, so this is the trickiest bit. So, fast autoregressive decoding. Autoregressive decoding, like I described, it's producing outputs conditioned on all of your previous outputs, as opposed to just the last one. And so what we're trying to do in sequence generation is, given an input sequence, a source sequence, we're trying to learn our map to our target sequence. I mean, one way to do this would be to just, like, in one shot, you're just going to go from entire input sequence to entire output sequence, like this, which is kind of what the equation above shows you. But perhaps another way to do this would be to use a decoder. And what it does is you encode your input, just like Kris described, just some function which kind of like distills the meaning of your input sequence. And then you run your decoder, which makes a single prediction, one prediction about what the output is. You then feed that one prediction back into the decoder, and then you run it again. And that gives you your second one, and so on and so on. So is there anything really obvious that sucks about this versus the one shot? N squared. Yeah, so does that make sense? You can't parallelize it. Yeah, yeah. So there's like this dependence tree or dependence graph where each of these lines depends on all of the previous ones. So you have to execute this in sequence, which at train time and at train time kind of sucks because we have to go one at a time, slowly pumping it through. If your sequence has 100 elements, it's 100 times slower than our one-shot generation that we really want to do. So we need to think about ways to kind of solve this dependence structure. Just out of interest, does anyone know what I'm going to say? Like, what's a good way to solve this dependence structure? Okay, sweet. So, I'm glad it's a surprise. What you can do is, at train time, we have access to our targets, which are kind of the gold ground truth of what we had hoped we had generated. So whereas here we are producing predictions and feeding them back in, well, one thing that we could do is instead of feeding in predictions here, we could feed in the targets, the things we wish we had have produced. And so now there's actually no dependence between the lines. All of them can be executed in parallel. But we still need to execute, let's say sequence length 100, we have to execute 100 passes of our decoder. And that takes a massive amount of memory. It's also, I mean, assuming you could fully parallelize, at least it takes a lot of memory. So we can do better. Okay, so the trick to do better is borrowed from stuff like WaveNet and Pixel CNN, where you basically augment your architecture of your neural network so that it can't cheat. And what do I mean by cheating? Okay, so if I have like this attention matrix, where my input sequence is a sentence in Kiswahili that I'm not going to try and read, and our target sequence is the corresponding translation in English, how do you think an attention mechanism could very easily cheat in this case? Kris already gave the answer in his first talk, so you should know. Do you have any ideas? Okay, no ideas. Okay, so, right, so the answer is, I have an attention mechanism here. I can basically reference anything in both of these sentences right now, and I've given it the true outputs that I want to produce. So of course, if I have the true outputs, I can just look at them, copy them, and return them. No learning necessary. Does that make sense? I've provided true target outputs when in reality, I would never have access to those, right? Like, in reality, what I'd be providing is my predictions. But here, it's like my gold ground truth standard. And so what I'm going to do is not even try to make any smart prediction. I'm just going to grab the answer, copy it over, and return it. I'm going to get 0 error. It's going to be state of the art. Yeah. So what it does is something exactly like that. It goes ahead, and for the first element of the input sequence, I'm just going to replace it with an external memory. It's incredibly complicated. and it's super interesting, but it hasn't got much use yet, I don't think. Like, very few people have the resources to actually train a neural Turing machine or differentiable neural computer, which was the follow-up work. They're also very tricky to train. So they're extremely difficult to optimize. I didn't mention this, but one of like the major selling points of the autoregressive architecture, the transformer, is that it's easy to optimize. It's like easy to train. It just tends to work if you throw no problem at it, which with RNNs, due to stuff like vanishing gradients and like all these other kind of architectural properties, it's not really the case. So coming up with architectures that are easy to train is really core to adoption and utility. Whether the NTM has achieved that is debatable, but it's certainly a very interesting first step in that direction. Kind of uncanny valley type samples of language. Yeah, like examples like this, like even the hand-chosen, you know, PR-ready examples from GPT-2, they make no sense. Like there's just like these breaks in logic. Yeah, what's been done to kind of rectify that? I think grounding is kind of interesting. So there's this idea of like, you need multiple modalities in order to really grasp what language is trying to do. So humans created language in order to explain the world around them, and then later on, language turned inwards. But if we're going to be starting on generating language, we can't just go from 0 to 1. We're wasting time. We're burning way too many resources on deep learning. We need to get back to symbolic and logic-based systems, which I kind of in part agree with. Like HYPE really does just homogenize the research directions and kind of directs resources into only one specific area, which I think is bad for research. We need diversity, we need like high-risk directions to take. But on the other side, deep learning isn't trash. It's super useful. It's the best we've got so far in a variety of domains. And if you're going to critique it, you need to propose concrete steps forward, which I think a lot of the dialogue coming out of these individuals has kind of lacked.